Hello, my name is Mohammed Awad. I'm an electrical engineer doing a research experience for undergraduates under Dr. Michael Vasiliev. Today I will be talking to you guys about the spatio-temporal pump shaper for all optical signal processing. This project was done with the help of Chen Guo. The abstract of the project: in linear fiber optics, we utilize nonlinear wave interactions in highly efficient optical fibers to manipulate the properties of the wave, and this is done by controlling the pump. In this project, we will investigate two properties: the spatial and the temporal characteristics of the wave. We did this using two experiments. The first one, the temporal mode generation using an optical intensity modulator, and the second one being a spatial mode generation using the spatial light modulator. The background of the project: nonlinear fiber optics utilizes the interaction of optical waves in a dielectric medium. In all dielectric mediums, the optical fiber proved to be the best due to its low loss as well as its long interaction and along its length. The spatial mode of the optical signal is determined by the core of the fiber, the diameter of the core of the fiber, and then the temporal mode is determined by the switching speed of the light source or the characteristics of the external modulator. For the principle of the temporal mode control, we have our input signal coming here from the left, which gets separated into these two arms. We have these three electrodes, the middle one being a positive and these outer ones being ground. This difference in potential creates a phase shift in each optical arm, which whenever they recombine over here on this side, it causes them to either constructively or destructively interfere. We also have this electrode over here on this bottom one, which allows us to choose where we start on this cosine graph. This blue highlighted part is shown in this part of the equation, which determines the temporal characteristics, and then this V bias, as I mentioned earlier, just determines where we start on this graph. In terms of the schematic, we started building the electrical side first. We have a 12-volt input coming into here that goes into a 12-volt to 8-volt regulator. This ensures a stable 8 volts going to our RF driver, as well as we also have a negative 5 volts just to give us that bias that we need to create our amplification. We also have a switch here to allow us to pick whether we want this amplification to be involved or not. We have our input RF signal going into the RF driver that goes to the intensity modulator, and then we also have our biases here on the back panel, and then we have our input optical signal going into the intensity modulator, and then our modulated output on the output over here. Our built prototype over here in this blue highlighted section is the VRF, and then this red highlighted section is our voltage bias. On the front here we have our two optical inputs, the optical input and the optical output ports, and then we have our VRF input as well as the switch, and then on the back panel we have our power and then our two voltage bias ports. In order to validate the prototype that it functions correctly, we have a tunable laser source go to a polarization controller that went into the intensity modulator, a pattern generator to send our function to the modulator, as well as a DC bias to ensure that we start on the V pi. And then we also had a trigger that went to a sampling oscilloscope to measure our signal, which gave us this optical or eye diagram. This shows us how clear we can read our signal with the horizontal space showing the distinction between a 1 and a 0, and the horizontal spacing showing us our jitter. This open eye shows us that it gives the intensity modulator gives us a clear reading. In conclusion, the temporal mode was packaged and completed and tested, And then for the spatial mode, we're still under development of that part of the project.